All right, so we should be live now, and give me just a second here. I'm going to wait for this video to buffer so I can hit pause on it so it's not distracting me. And so, yeah, again, start on page 8. There we go. And now let me minimize that so I get less glare. Okay. So I'm going to just kind of review some stuff that we talked about last time. So in this case, you remember there was power, there was momentum, there was pressure, and then there's density. So this is power, momentum, that's chapter 9, momentum is. This is pressure, that's chapter 14, and density will probably focus on it mainly in chapter 14 as well. But density is sprinkled throughout all the chapters. So those are kind of our basic letter P's that we have to work with. And so we're going to talk about these more later in some other chapters. So in this case, I don't know if you remember, the definition we said was the time derivative of energy. So it's taking the derivative of energy with respect to time. All right. And so in this case, we could say that power average is equal to delta E over delta time. All right. So now in practice, it would be ideal if we know the energy is a function and you could take a derivative of it, but sometimes we can only get this approximate value. And even if you slice up a problem into tiny time steps, you're still usually using this average power result. All right. Now, sometimes we saw that power could be work over time. All right. And so this is another good way to think about it. Remember, work is like change in energy. So this is okay. And then we also saw there was a shortcut, power instantaneous is equal to force dot velocity. So these again are on page 8. So that was power, and I don't think we had time to do that much with it. So I wanted to talk more about that today. Whoops, that's the wrong one. Let's go to this one. There we go. All right, and so I think we were a little bit down below that. Apologies for some scrolling here. All right, so there was all the kind of things that we were talking about. And I don't think we did this problem last time, so I wanted to kind of start with that and give you an idea of how this might work out. So we're going to start with 7.9. If you want, you could write that one up. So in 7.9, what do we know? Let's see, there's something hanging here. We know it's going to rise up some distance h in some known time t, and we know that it has mass m. And we know it accelerates upwards from rest. Okay, got it. The first part of this problem says, determine the acceleration. What does your gut tell you to do? What type of problem might we try here?
Just a normal force problem?
FBD. We could. And so FBD. However, I want to point out, do we know the acceleration? No. Do we know the tension in the cable?
No.
So that's going to be tough. So that's a great idea. I would have probably first tried to do it exactly like you, and I just know from experience that's not going to work in this case. Is there another way to get the acceleration? The force trick doesn't work in this case. Force tool.
2D motion, or will this be 1D motion?
I guess 1D motion. You could do 2D motion, and then the motion in the horizontal direction is 0, which gets us back to 1D. So 1D motion. Let's take a look at that. Okay, so part A, I could use the delta y equation. Got it. Now take a look. In this case, V initial y is what?
0.
0. What were the key words in the problem, Alonzo? That told us that.
Rest, upwards from rest.
Yeah, it accelerates upwards from rest. Nice job. So we know that that's 0. All right. And so from this, hopefully I don't screw this up. Hopefully you agree that I think if we solve for AY, you get AY is what? 2. The distance is h, and then it's over t squared. So that's nothing too crazy. Got it. How about part B? Part B asks us, determine the final speed. What do you think? What should we do? What do you think? You can throw it in the chat if you want.
Could it be the v final squared equals v initial squared?
You could, or we could, yeah, it's basically another kinematics equation. Seems like the best way to go. You could try and do work and energy, but we don't know the forces. That's a bad idea. So I'm going to do V final equals V initial in the y plus A sub yt. Now in this case, I don't need the V final squared equation, but you had the right idea there. Whoops, that's not 2. The initial is 0 in the y. So basically it's multiplying this number by 2. So we see that V final y should equal 2h over t. Notice it's not distance over time. So the final velocity is actually larger than distance over time. Distance divided by time would get the average speed. So we see that the average speed would be h over t. And notice the average speed for a constant acceleration problem would occur half the distance up. So we see that the speed at the top is exactly twice what it is at the average, halfway up. All right, so far so good. Part C asks us to determine the tension in the cable, right? So part C, we're supposed to get the tension. So how could I get the tension force? What type of problem?
Now we can do an FBD since we know the acceleration.
Exactly. So we got tension here. We got mg down. And then this particular one, I think, is accelerating up with some rate. I'll just call it A sub y for right now because I chose to call it A sub y earlier. So I think what we see is tension minus mg equals m ay. And anytime you have this one, I know it seems silly, but it's always worth checking. This force and the acceleration should have the same sign. This force and acceleration have the same sign. Looking good. So out of all that, maybe I'll rewrite this with some color here. All right. Oh, and I can get rid of, whoops, I can get rid of this one to get rid of some glare, a little bit at least. Sorry, that's still a little bit of glare. There we go. All right. Sorry about the glare. All right. So in this case, we see that we've got the tension, we've got the acceleration, we've got the final velocity, we've got all these parts. Now, just to kind of speed things up a little bit for the last half, I'm going to summarize those results so I can use this top part of the board. So I'm going to try and summarize that stuff up here, and then we could go on to part D. If I'm too slow, you can always read part D. But I found that AY is 2h over t squared. I found that V final y is equal to 2h over t. And then we found the tension was mg plus m. I'll just leave it in this ugly form here. Who cares? We could see where everything comes from if I write it in that way. And now I can erase the board. So we have some room to work. So far, so good. Next, determine the average power delivered by the motor. All right. So in this case, there's a couple of ways we could go about this. All right. So we could get energy final minus energy initial divided by time. Now, this would get the net power from the entire system. And where this problem gets a little bit confusing, I want you to think about it like this. As you're lifting this object up, or as the cable is lifting it up, the motor is exerting that tension force. So really, the work done by the motor would be a better thing to use up here in the numerator. So because as we'll learn in chapter 8 in a few minutes, this change in energy is a little bit subtle to talk about. So for now, how about I write it like this? Let's say this is work done by tension. And this is probably the better way to do it. So again, there's a little bit of subtlety. By the end of today, you might understand the subtlety and we could revisit this problem. But for now, let's get the work done by the tension force. Well, I know we're going upwards distance h. So the displacement is h in the positive j hat. I know the tension force is upwards, and I know its magnitude. So that just means multiply the tension magnitude by h times the cosine of the angle between. So that's T. That was a lot of words. Let me just show you what I mean. T H times cosine of the angle between, all over the time. This should get us the work done by this force tension, which ultimately is coming from the motor. All right. In this case, what's the angle between these two?
Zero.
Zero. What's cosine of 0?
1.
Yep. So that means it's basically T times H over T. So it's going to be mgh plus 2mh squared. And then let me do it this way. This is divided by T, and this will be divided by T cubed. So let me make sure I didn't just gloss over something here. Let's take a look at it. This is the tension, and I need to multiply by H and divide by T. So the tension, I get an mg H over T on this term, and here I'm getting an H squared over T cubed on this one. What's something we should do with any problem when we get an algebraic answer like this?
Check the units.
Check the units. So in this case, what are the units of power?
Watts?
Watt? Yes, watt. So a watt, what's another name for a watt?
Is it joules per meter?
Joules per, remember, it's energy per unit time. You were on the right track. Joules per second. Nice job. Okay, and then what's a joule? It's a real gem of a unit. Do you remember?
Is it Newton meters per second?
Careful. A joule is a Newton meter.
Oh,
So a watt is a Newton meter per second. Another way you could remember this is if you ever forget, you can flip your book over to the back and read the equation sheet and just find any equation that you know has units of joules. Now, at first you may say, whatever, but when you get to physics 163, this is very common. So you flip to the back of your book, you find an equation that you know has the correct units and use that to deduce the units. That said, it's a Newton meter per second. Now, I could actually use this to check. So I know, well, actually, let's go one step further. What's a Newton? In terms of kilograms and stuff.
Kilogram per meter per second squared, under a second squared.
It's a kilogram meter per second squared times meter per second. Now, notice we probably could have jumped right to that if we had remembered that it's force times velocity for instantaneous, right? So sorry, there's a little bit of a glare there. The instantaneous power is that's just a Newton times the velocity. But I hope you agree there should be kilograms on top, meters squared on top, and seconds cubed on bottom. Well, this has got kilograms, meter per second squared per second times a meter. That's correct. This one, kilogram, meter squared, second squared, the units check. So, okay, you could take a little bit more time and do that, but I just wanted to point out the units do check and we could go through this process. Excellent. All right. That was the answer, I think. So we've got that one. And then lastly, part E says determine the instantaneous power at the second it reaches the top. And so I need to erase this. We've got our answer here, but I need just a little bit more room. And let's lower this down. So power instantaneous, we could use the equation force dot V. Well, in this case, that's just tension in the J hat dotted with V final Y in the J hat. And very similarly, we could just go up and grab the two pieces, multiply them together, and we've got it. We have an equation for tension. We have an equation for V final Y. You plug it all in, you get the answer. And maybe I'll just go to the screen share for this one. Oops, that's the wrong one. We want 7. All right, and so there you go. We get this weird result. But notice the instantaneous power at the end is twice as big as the power output on average. This makes sense. Initially, this thing isn't moving at all, right? So you haven't done any work yet. So there's basically 0 power output at the beginning because you don't need that much to get it going from 0 to 0.1. And then to get it going from, say, average speed up to very high speed, the peak speed, there's going to be even more power required. And so the highest power output is actually right at the end in this case. All right. Nothing too crazy there. I'm going to pause. Any questions about that?
so instantaneous power is the dot product between a force and velocity, right?
Correct. That's
Okay.
one way to get it. The other is if you happen to know a function for energy as a function of time, which we don't usually, you could take the derivative of it.
Gotcha. Okay.
That force dot velocity tends to be a little bit easier for what we're doing right now. Okay, moral of the story, just looking back on what we did in this problem, you get an acceleration, a velocity. From that, you can figure out a force. You can get the work done by it, and you can get the power in any way you want. So if we wanted to understand the power involved with some object that's moving around, this process would work. All right, so next, I know this may seem a little bit silly, but I'm going to show you the next problem here and talk a little bit about it maybe someday. My screen share ever worked. That's volume 2. Now, this one is a little bit different. I want to talk about this one a little bit, and maybe I'll go up here to 250. All right, let's get this all on here. So I'm looking at 7.10. All right. So in this case, at first glance, this problem seems like some stupid thing a physics teacher just pulled out of nowhere and just made up, which is exactly true. However, let me run it by you like this to show you why you might actually find this interesting. What if we took a video of something and we watched it move around, and then we used video capture technology to plot X as a function of time, and we figured out a trend line. So we pumped the data into Excel or some other spreadsheet or something and did a curve fit. And from the curve fit, we just kept playing around until we found some mathematical function which approximately models the motion. If we could do this, we could get an equation of motion like this for any random object you like. So it could be your car driving, it could be an animal running, it could be a person swinging, or it could be all kinds of things. So this is actually a realistic thing that could be done. A person could figure out some random X as a function of time, and it could have all kinds of weird exponents and powers and things, whatever. All right. And if we know the mass of this object, follow me here. Always check the units, fine. Just like the last problem, we could get velocity and acceleration. After that, we could get the force, just like last time. And then we could get either the instantaneous or the average power. And so what we see in 7.10 is you could take a video of an object, get an equation, and figure out the horsepower associated with that motion, or whatever you want to call it, how many watts are being exerted. And so there is a useful problem. Now here you have to think a little bit. And so notice here, the average power, in this case, you would probably want to use the change in energy over time, because we know the velocity is a function of time. We could get the initial velocity, the final velocity, crank it out. We could get the instantaneous power at this time by plugging in t equals 2 to these numbers. We've got the velocity at that point in time, etc. So there is a purpose to this. I'm going to pause. Any questions on this one, or the worth of this, or why I would do this? Anything at all?
You mentioned horsepower for the last one. Is that an equivalent of power? Is that
horsepower is a unit? It's related to watts. Yeah. So you could Google convert horsepower to watts. So
okay.
And let's see if we've got it here. Oops, sorry, that's something I'm doing for you guys later. There it is, 746. Got it?
Yes, thank you.
Seven. And so it's basically just it's a strange unit, isn't it?
Yeah.
Who cares about that? Yeah, good question. Others?
Mm-hmm.
So think about, there's often, maybe you've seen a lot of motors are sometimes like quarter horsepower or something, right? And so you could even have fractional horsepower, which, you could also just give a watt. So it's a quarter horsepower would be about 200 watts. Yeah. All right. I guess you could rate light bulbs in horsepower, right? So a light bulb would be 100-watt light bulb would be approximately about a 0.13 horsepower light bulb. I'm going to start doing that just to be really even more annoying than I already naturally am. All right. Okay, that's a good way to not get anything successfully completed, by just being a jerk, right? Okay. All right, let's get back into here and get out of this chapter here. Whoops, let's get into this one. Yeah, and I'll check the chat in just a second here. Yeah, for sure, will do. All right, let me just outline a couple of things about some of these remaining problems here. And let me make this about 225 so I can see it better. All right, there we go. So A car drives, and here's an interesting problem. You have a car driving on flat ground with some speed. Obviously, air resistance is not negligible for a real car problem. And you could say, okay, let's say the car output is this. Notice if you want to, if the car drives at the same speed up a hill, we would assume the air resistance is unchanged. And you could actually figure out the factor by which power has to increase. So we may not know the power output of a car, but this would show us a way you could use some ratios and be clever to figure out how much the power output should increase. All right. In this one, we talked about this one already last time, but let's review it again. Sorry for the italics. Again, I fixed that for next time, but it's too late now. So in this case, there's a car. This is decoy information, most of it. The idea here is if you know the initial kinetic energy is 0 and the final kinetic energy is 1/2 mv squared, we know the mass, we know the final speed, and we know the total time is 10 seconds, you can get the average power output, and you don't have to split things up into stages. So that's an interesting one. This one is kind of cool. Suppose you have a power lifter and she's holding some mass in front of her face, and she's going to use a 3-stage process. Now, look at this question. This ties together all kinds of stuff. And notice I ask you to sketch the plots. You don't have to be perfect, but right, are they sloped up, downwards? Are they curving, flat, etc.? So this is a good review because to understand a plot of these things, you really have to understand a lot about it. So we have to do kinematics, forces, energy, and power. And so you could actually figure out all these factors and sketch them, and that would see if you, the scale reading versus time. So this would be a very interesting thing to do, and you could see if you really understand them. And you don't have to, beat yourself up and try to be perfect and plot everything in Excel. Just sketch it, and then you could see. And then, think what happens, what's different if she lowers them instead. So I'll let you look at that later. And then this one requires separation of variables, so we probably won't spend time on that. But if you're curious, this is a cool problem to read. So we've talked about what happens if you have constant force, right? What if you had constant power? Constant power output is not the same as constant force. Case in point, remember up here, we saw that the power on average was not the same as the instantaneous power. So just because you have constant forces doesn't mean you're going to have constant power. So if you're curious, what if you do have constant power? Then this problem is for you. Okay, so if you could have constant power being applied to an object, what would the curves of position versus time and acceleration look like? All right, so if you're curious about that, there you go. I'm going to pause there for a second because I think we're ready to go to the next page. Yeah. So any questions about that? Just checking the gallery view. All right. I'm going to keep going. Feel free to interrupt me at any time. Feel free to interrupt at any time. All right. So now force distance trade-offs. All right. So I want to talk a little bit about this. And then we'll be pretty much done with this chapter. So, all right, we're going to start. We better read this carefully. There's a lot of subtleties in this one. So, okay, we're going to raise a box from the ground. The goal is to get it on this loading dock here that's some distance h above the ground. Now, I'm going to make some assumptions. I'm going to assume the box is lifted at constant speed to simplify the problem. Obviously, this is impossible. Right? The box starts at rest, then it's going to speed up and start moving upwards, and then it's going to come to rest again. So obviously there's 2 acceleration stages, speeding up and slowing down. However, if we move the box slowly, the acceleration stages are going to be very short compared to the rest of the problem, and we could basically ignore the acceleration stages. And if you think it's not, if you think that's not appropriate, well, I could say, okay, well, make the velocity even slower. Make the velocity 1,000 times slower, and then it is approximately true. So basically, we can do this. We can move this box at constant speed and just have that speed be very slow, and the acceleration phase is very short. Great. Okay, so now let's think. Let's say person number 1 lifts the box straight up. If we're moving this at constant speed, what force is required? If this is at constant speed, what's the acceleration for this case?
0.
0.
Okay, so what's true about F1 and mg? Don't overthink it.
They're the same.
They're equal.
Yeah. So again, this is the approximation we're making. We're assuming force 1 is just magnitude mg because acceleration is effectively 0 by moving this at constant speed. Great. So what's the work done for force 1? Well, if you recall, that's going to be force 1 times the distance, which is h, times cosine of the angle. What's the angle in this case?
0.
0. They're both going straight up. So notice the work done by force 1, if I plug in all this crap, is just mgh. So that's kind of just for reference. If you lift this block up, mgh is how much work is required. Great. Now I'm going to try and slide this down just a little bit here. Now we're going to have this other case where the person pushes horizontally. Okay. And they're at this weird angle. Now, this might not, I don't know. So maybe this isn't obvious to you. But in this case, I should still be able to use this equation. Work 2 should equal force 2 times the distance. In this case, the distance is the length of the ramp. So it's not h anymore. It's the length of the ramp. And then I'm going to have to do cosine of what angle in this case?
19.5.
Yeah, 19.5 in this case. If you don't believe me, give me just a second and I'll show you. So, right, the force is applied this way. The displacement is right up there. And hopefully you can see that should be exactly the same as the ramp angle. So that's where this 19.5 shows up for this one. Now, when I punch in, I'd have to do an FBD for this object too, right? So let's do that FBD. F2 is this way. Is there friction here or are we ignoring friction? Frictionless, frictionless. So we don't have to worry about friction. That's cool. There's mg straight down. And then there's also the normal force kind of off this way a little bit. Sorry, it's a little crooked there. Now, in this case, just so I could see things a little better, I'm going to split up F into components. I hope you agree this side right here would be F cosine. I'll just call it theta for right now to save my time. So there is kind of the deal. Now, we could actually get this result of work number 2 using this equation up here. I could actually say I could group the force and the cosine into this one term, force parallel. And notice this F cosine happens to be the force parallel to the displacement. So that's just another way of showing you the same thing. Great. Now here's the crazy part. If you do all the math on this, set A equal to 0, blah, 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 work 2 happens to equal mgh. If you want to, you could see that that comes from the fact that, well, yeah, it's a little bit complicated. I'll let you go through it all and see. But the work done in number 2 is actually exactly the same there. All right, so what is going on here? Well, this is called a force-distance trade-off. The short distance, the red path or the upper path or 1, and this one, That's just a direct shot. Just lift it up and put it right on top. Well, that's great. You need to exert this force, mg, over just this small distance h. If we use a ramp, we can use a smaller force, F2, but over a longer distance and get the same result. Now, this is not, there's some subtleties to this even still. We'll get to those in a minute. But the idea here is if you apply a smaller force over a longer distance, you can get the same amount of work done. All right, questions on this?
So how do we know F2 is small? Oh, just the arrow size?
Well, let me ask you this. Do you agree that that 20-degree angle basically is pretty small?
Yeah.
Yeah, and so now in this case, the normal force is supporting a lot of the weight. So that means to get this thing to move horizontally, we probably don't need that much applied force horizontally. And in fact, we could see it like this. Maybe you could see if I split this up, do you agree the horizontal component, F cosine, only needs to equal mg sine theta?
Oh, yeah.
Do you agree that right, again, acceleration is 0. So that means the force up the plane has to balance out the force down the plane. So F cosine theta is mg sine theta. But sine theta is a number less than 1 when you plug in 19.5 degrees. So far, so good?
Yeah, that's cool. Okay.
Yeah, and from that, you could probably see, oh, I bet the length is something like, okay, the length relates to, yeah, the angle as well. And so all the cosines and sines end up dropping out and you get this cool result. All right, so that's that one. Other questions? All right. So now in this case, what is the point of this, right? The idea is, well, in the real world, some objects are so heavy, you can't lift them. So in some cases, this force is too much. It will destroy your body or your back, or it will break the device that you're trying to lift it with or whatever. So by using a ramp, you can lower the amount of force and get the job done. Now, here's what's crazy. Obviously, whoever's lifting this box had to eat some Snickers bars to get this job done, right? Or some cookies or some kind of high sugar. Otherwise, this box is never going to get lifted. Now, your body is burning that sugar. And the amount of sugar you burn is probably a lot larger in this case. So even though the amount of work done on the box from a physics standpoint is equivalent, the amount of work your body has to do may actually differ because you may end up using more chemicals to flex your muscles in these other ways. And there's friction and there's other things in life too. So in the end, sure, you may have to expend a little bit more energy from a practical standpoint to get this up here, but the work done on the object is the same and the problem is actually doable. If you use the ramp, you could probably get the block up there, whereas if you try to just lift it off the ground, maybe you can't do it. So regards to that, let me mention this here. I'll come back to this in just a second. But so the idea here is if you do problem 7.16, I allude to how much work was done on the object and then how much energy was used by your body in terms of how much sugar you had to use to get your muscles to work. So the work done inside of your body to make your muscles flex is not always the same as the work done on objects in the real world. So 7.16 will help you understand that process. All right. Now, in this case, there are other types of devices or machines we could use. So a machine is a device used to change the direction and or magnitude of a force, right? So think about this case right here. You're applying this force horizontally and effectively it causes us to get this component up the plane. So it's changing that direction and the magnitude of that force. So that's what the lever is doing. It's a machine that changes the force from horizontally applied to up the ramp. Now, there's other ones, a screw, a wheel, wedge, inclined plane, and pulley. Okay. Oh, I guess you could call, excuse me. I think I called this a lever. I should have been calling it the inclined plane. I'm sorry about that. But yeah, so we've got this inclined plane. Now you could say, what's the difference between that and a wedge? All right, whatever. A wedge is two inclined planes back to back, say, but if you're a mechanical engineer, this might interest you. If you're a mechanical engineer, you could start, so here, say a wedge is essentially two inclined planes put together back to back. You could try and imagine different ways you could use each of these objects to get it up the hill. Now, the most popular one for us is probably the pulley. So I actually have a video of that in just a second. But before we talk about that video, any questions about these machines? Okay, a machine is basically one of these things or a combination of some of these things. All right, let me clear out these annotations and find this video. Is it this one? No, it's not that one. All right, is it this one? Yes, it is this one, but let me get it over here. All right. Oops. Maybe I thought I hit the, what's going on here? There we go. All right. So I'm going to start here. So this is a version of a block and tackle. So whoops, let's get right in. Whoops. Oh my gosh, come on. Are you kidding me? What? How did I get here? All right, hold on. I hit the wrong button. Apologies. We'll get back there. Where is it? Come on now. There we go. Sorry about that. All right, so here's a block and tackle. Now, in this case, there's a string running like this, and it goes over a pulley, it goes down, and it goes around this pulley, and then it connects up here. And so basically that upper pulley has a string coming down this way, has a string coming down this way, and then there's a string attached to the axle as well. Furthermore, there's a support string going upwards that connects it to the ceiling. All right. Now on this lower pulley, what do we have? On the lower pulley, we've got a string going up on one side, a string going up on the other side, and then we can hang a mass off of it. So let's think this through. If you hang a mass on here, how much tension, and we just try and support it, not even accelerate it. So let's just we try to support it or even move it with constant speed. What should be true about the tension in this cable?
Each one is mg/2.
Exactly, half the weight. Now, that is the same as all of these. This is T, this is T, and this is T. So what does the upper one, how much load does the upper string have to support? So this string up here, what does that have to support? How much of the weight?
All of it. So 2T?
So,
Or is it 1T?
nope.
E, yeah. Just
Yes.
mg.
Nope. What's tension? It's the same string. You just told me what the tension was.
mg/2.
So how much does the upper one have to do?
mg/2.
Times 3.
No. Oh.
There's 3 strings pulling down, each with mg/2. So I need 3 mg/2s. 1, 2, 3. Does that make sense or not?
Oh, yeah.
Aren't you holding one of the strings too?
So I'm pulling down on this string and I have to exert force T, right? If I'm not pulling on the string, there's no tension. And so let's get in here and look at this one. Let me play this one and let me see what my speed is at. Okay, we're at normal speed. Okay, let's skip forward a little bit. All right, so this is a good spot to kind of see it all. Let me move this. Let me hit Control Alt Shift H. That hides my zoom controls. All right, so now, I just hid the controls I need to show you stuff, but look at the string, right? It goes around the top pulley. I hope you could see my mouse right now. Then it goes around the bottom pulley, and then it hooks to there, and there's a knot, and there's a scale up here. So we're going to actually be able to read the scales, and you can see I'm not full of it here. All right. So in this case, right now, I've set it to 0. That's just showing you that I zeroed everything. And now everything else is at 0. And so this is going to be where I pull. I'm going to pull on the scale, and you can see that the force I exert in my hand is also that tension. Notice I'm pulling this down here, and I'm going to connect to that big heavy mass. Now, I don't know if you can see those 2 white marks that I just pointed at. The idea here, I hit pause for a second. I'm going to go from this upper white mark all the way down to that lower white mark. That's 1 meter of travel. So I'm going to try to pull the string for 1 meter at constant speed and have negligible acceleration stage. All right. And then when I do this, sorry, let's skip ahead a little bit. Okay, so notice this is the mass I'm going to use. It's about 11 pounds. So I'm using an 11-pound mass. So think to yourself, what should the tension in the cable be if we have an 11-pound mass? Approximately, give me a number.
5.5 pounds.
5.5. So that's our reference. The mass that we're trying to lift is 11.5 pounds. All right, so let's keep rocking here. You can see that nice bald spot. That helps enhance the physics. Bald spot enhances the physics. All right. Okay, dude. Get it? Oh, he could successfully hang a mass on a hanger. All right, here we go. Let's get to it here. All right, sorry, there's a little slow here. I was talking in this video, and you can watch it online. So now, again, I'm lifting it. Notice the knot was up at the upper white mark. I'm lifting the knot all the way down to the lower white mark, or approximately down there. It's not exact. There we go. I got the knot all the way down. You see that? Whoops. Notice it says 6.5 pounds, not 5.5. Okay, fine. But that's about right. Okay. Now the other scales should be locking in place. I was waiting for them. They have a mode where they'll lock. We know that one's 11 pounds. It only took me 6 pounds, or about 6.5 pounds of force to lift this thing, but we didn't get something for free. I hope you noticed that lower mass moved half as far, right? It doesn't move a full meter. It only moves about 50 centimeters. So that's me showing you that. It goes from whatever, 30 to 80 or something like that. I forget what the numbers were. But so it moved 50 centimeters, even though the other rope that I pulled moved 1 meter. Sorry, this is taking so long. We're almost there. And then up to the top, I don't know if you can read that number on top. It's 18. Okay. So in this case, do these numbers make sense? Okay. We saw that, again, if I could get my annotations back, we expected the tension should be about 5.5 newtons. Or wait, 5.5 pounds. We're in units of pounds for this one. We expected the tension upper, I'll call that tension from the ceiling. That should be about 3 times that. So 15 plus 1.5. So that should be about 16.5. In practice, these numbers do not exactly match up. Why? Because there's some friction in the pulleys themselves. You could argue this rope is not really a string, so maybe there's a half pound of string there that we had to lift up. So in the end, we do see that this number works out. Okay, exactly. So if you have to lift a heavy object, what are the pros and cons here? You can apply a force that's much smaller over a much longer distance. So, for example, if you want to lift an engine out of your car, that's way too heavy for you to just lift. So what you could do is you could make a block and tackle, and you could actually use more pulleys. And then the idea is you get a really, 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 really long rope or chain, right? And then you could pull a whole bunch of chain over and over and over. And then you could raise the engine block very slowly by applying a force that a normal human could lift. And then once you get it lifted, you could tie that chain to a small object and it won't go anywhere because it takes very little weight on the other end of the rope to keep this thing from falling down. So it's a practical force distance trade-off. All right. Woof. Questions on that? It's kind of cool, right? I don't know. I think so. Okay. You're not getting something for free. All right. Regarding that, let's go back to sorry, we're almost done with this chapter, but I just wanted to be thorough here. Let's see. What do I want? I want this one. All right. So if you're curious, I'll get over into here. Here's a kind of a fun one. This is one I like to think of, and I'll go to the whiteboard for this. So imagine you have this one. Imagine you are driving your car out in the woods, okay? And you get stuck in a mud puddle, right? And your car just is not going anywhere. You're by yourself. You're, say, 50 miles from the nearest road, and you don't want to have to walk and hitchhike, which I have had to do before. All right. So it makes for a long, long, long day. Okay. So what do? Your car is sitting here stuck in something in the mud. Fortunately, you happen to bring a rope, and fortunately, your car happened to get stuck in a mud puddle right next to a tree. This is a lot of fortunately's here. You have to get kind of lucky, or a giant rock. But the idea here is you could actually tie a rope from the frame of your car, not the bumper, around the tree or rock or whatever is has mass very large, okay, a movable object. Once you do that, you could come into here and actually apply a force perpendicular to the center of the rope. And when you do that, you basically get a force multiplier. This is effectively a lever. Now, when you do this, right, you're going to apply a small amount of tension here that gets magnified in the other component. Huge magnification. Cool. So the idea is you push on the center of the rope, you get your car to move. The trade-off is you apply this tiny force over this large distance, and then each time the rope, each time your car moves a few inches, you've got to untie the rope and retie it and get it tight again. But it beats being stuck out in the woods. So that's an application I thought was kind of fun. In theory, you could actually use this as a magnifier to exert a force and get yourself unstuck in some weird situation. So again, by using physics, you could try to apply a force in a clever way rather than just trying to pull your car out. But again, you have to have the right set of circumstances to be able to use this trick. So there's another cool one. And so if you're a mechanical engineer, you might actually read through these problems. This is the kind of stuff mechanical engineers might get into. Here's another one. You could use a winch. All right. And the winch is pulling cable at a constant rate. So this one looks really nasty. You could try and figure out the speed of the cart. And it turns out if you're clever and think about the fact that the work done by the winch is equal to the tension times the length of rope pulled, you don't have to do a lot of crazy effort in this problem. So, oh man, yeah, let's leave it at that. So basically we see, I'll just show you this really quick, and then we'll call this break time, and then we'll go on to the next one. So, all right. So now in 7.18, a lot of students would try to do some big, ugly mess. Yeah, and it turns out you could try and do these integrals because the force is changing as the angle changes, right? So you could, look at that integral you'd get to do. I basically said, I'm not doing this problem. That's good enough for me. So you know it's bad when I'm too lazy to finish it. So at this point, you could actually do these problems. However, there's a shortcut where you could just use the work energy theorem, right? You say the work energy theorem is tension times the length of cable pulled. You could use some math to do this. And yeah, this beats doing integrals. All right, so I'm going to leave it at that. And so it's 5:30. We should take our break now. But are there any questions before we go on break? It's kind of interesting, but there's a lot of grinding to do. All right, so I'm going to stop there, and I'm actually going to stop the live stream now, and then I'm going to start a new one for the next chapter, just because this is a good break spot. I won't